Hello students, in last class we have already discussed some basics of how to design main component of G+3 RCC framed building. Now in this lecture we are going to design each components by taking an example. A typical floor plan of building is shown in figure has the following data. Type of structure, multi-story rigid jointed frame, number of story 4, that is G+3, height of plinth 1 meter above ground level, floor to floor height 3.35 meter, internal walls 150 mm thick including plaster, external walls 230 mm thick including plaster. External wall is also called support width. Bearing capacity of soil is 200 kN per meter square. Loads floor to floor finish equals to 1 kN per meter square. Floor live load equals to 4 kN per meter square. Roof finish equals to 1.5 kN per meter square. Roof live load equals to 1.5 kN per meter square. Design the multi-story building using limit state method. Therefore, we have given some particular floor plan data and asked to design building using LSM. First of all, on seeing this plan, we should know which one is one-way slab and which is two-way slab. And this I had explained in last lecture. In this, those who are marked by S1 is one-way slab and those who are marked by S2, it is two-way slab. Moving ahead, today we will design one-way slab and other components will design in next classes. According to this floor plan, two types of slabs are there, that is one-way slab and two-way slab. Therefore, first we will design one-way continuous slab. Step number 1, effective depth. Effective depth is calculated according to IS 456-2000, page number 39. This is used for finding effective depth for one-way slab. In this, formula used is span upon depth ratio equals to 26 into modification factor. Span upon depth ratio is taken 26 for continuous slab. Modification factor is assumed 1.3 if it is not given in question. For percentage of reinforcement 0.4%. Therefore, L upon D effective equals to 26 into 1.3. Here, L is always taken as shorter span of one-way slab. Now, from this we will get D effective equals to 85.47 mm, approximately equals to 90 mm. So, we get D effective equals to 90 mm. Now, we will calculate overall depth. It is denoted by capital D and we had used formula D effective plus 5 by 2 plus clear cover. Here, phi is diameter of bar, generally assume it 10 mm. Clear cover is 20 mm. Phi is 10 mm. Now, on putting these values in formula, we will get D equals to 115 mm. D is overall depth. Now, we will move to step number 2, effective span. Effective span is calculated from IS 456-2000, page number 34. Condition used is support width is less than 1 by 12 into clear span. Therefore, we have to use these two conditions and will get two values. Clear span plus D effective, center to center of support. Whichever will be less is called L effective. Now we will calculate clear span. Clear span will be calculated from this plan. We had given in this plan center to center distance is 3000 mm and support width is given in question is 230 mm. Now we will calculate clear span. Clear span will be 3000 minus support width, half of support width minus half of support width. That is 3000 minus 230 upon 2 minus 230 upon 2. We will get 2770 mm. Now we will put these values in this condition which was given in IS code. So, support width that is given in question 230 mm is less than 1 by 12 into clear span 2770. Therefore, 230 is less than 230.83. Now, we will use these two conditions. Clear span plus D effective equals to the value of clear span is 2770 plus D effective equals to 90. So, we will get 2860 mm. Center to center of support is given in question is 3000 mm. Now, whichever is less is called L effective. Therefore, L effective equals to 2860 mm or 2.86 meter. Now, we will move to load calculations. In load calculation, first of all, we will calculate dead load. Dead load is calculated by using formula self-weight of slab equals to overall depth into density of concrete. This formula is given in IS code. We can use IS code. Now, overall depth value is 0.115 into 25. 25 is density of concrete and overall depth is calculated in last slide. Now we will get self weight of slab equals to 2.875 kilonewton per meter. Now floor finish which was given in question is taken as 1 kilonewton per meter and total dead load will be 3.875 kilonewton per meter. Therefore, factor dead load equals to 1.5 into 3.875, that will be 5.81 kilonewton per meter. Now, live load. Live load equals to 4 into 1 equals to 4 kilonewton per meter, that was given in question. Factored live load equals to 1.5 into 4, there equals to 6 kilonewton per meter. Now, we are moving to next step, calculation of bending moment. From this floor plan, we had taken a continuous slab A, B, C, D, E, X, Z. We had assumed these points as A, B, C, D, E, X, Z here. Now, A and Z are end supports, B and X are next to end support and rest all are interior supports. And following are the mid-span notation, that is F, G, H, I, J, K. From this, F and K are exterior span and rest other are interior span. Now the reinforcement at exterior span will be same to symmetry of the structure as well as their bending moment coefficients are also same, and the reinforcement in the interior span will be same because their bending moment coefficient are also same. Due to symmetry of the structure, we had taken only a particular section of continuous slab because the calculation is same for the rest of the section. In this way, we will draw this table and fill all values of dead load coefficient and live load coefficient from table number 12 for calculating bending moment. Now for the calculation of dead load coefficient for F, which is near middle of end span, is plus 1 by 12, and for G, H and I, which is at middle of interior span, will be plus 1 by 16. Now for the calculation of dead load coefficient for A, which is end support, will be calculated by adding dead load coefficient of F plus 1 by 12 and 1 by 8 from WL square by 8. We will get value as 1 by 24. Now for live load coefficient for F is plus 1 by 10 and for G, H and I is plus 1 by 12, and for A it will be the sum of 1 by 10, that is from F, and plus 1 by 4 from WL square by 4. We will get value as 1 by 20. Dead load coefficient for support V will be taken as minus 1 by 10 and support C, D and E is taken as minus 1 by 12. And live load coefficient for support B will be taken as minus 1 by 9 and support C, D and E is taken as minus 1 by 9. Now negative sign at support will be because of hogging bending moment at support, and positive sign at mid span is because of sagging bending moment. Now from diagram we can draw deflected shape of beam. At all supports hogging comes and hogging is negative, and at mid span sagging and it is positive. We have to calculate bending moment at every point for different cases. For example, for F it is the case of span moment. Now we will calculate bending moment at F middle span. Bending moment due to dead load is calculated from formula plus 1 by 12 into 5.81 into 2.86. 5.81 is called factored dead load. It is calculated from step number 4. Now 2.86 is effective span. Now we will put these values in formula. We will get 3.96 kilonewton meter. Now bending moment is calculated due to live load is given in formula. We will put values plus 1 by 10 into factored live load, that is 6, into effective span, that is 2.86. We will get value 4.91 kilonewton meter. Total bending moment is 8.87 kilonewton meter. Now we will calculate bending moment at B. Bending moment at B is next to interior support. Now bending moment due to dead load equals to minus 1 by 12 into 5.81, that is factored dead load, into 2.86 square, that is effective span square. Its values comes minus 4.75 kilonewton meter. Now bending moment due to live load equals to minus 1 by 9 into 6 is factored live load into 2.86 square is effective span square. We will get value equals to minus 5.45 kilonewton meter. We will get total bending moment equals to minus 10.20 kilonewton meter. Now we will calculate bending moment at G. It is interior span. Bending moment due to dead load equals to 1 by 16 into 5.81 into 2.86 square. Here 5.81 is factored dead load and 2.86 square is effective span square. We will get value 2.97 kilonewton meter. Now bending moment due to live load equals to 1 by 12 into 6 into 2.86 square. Here 6 is factored live load and 2.86 square is effective span square. We will get value 4.08 kilonewton meter. Total bending moment is 8.87 kilonewton meter. Now, bending moment at C. It is interior support. Now, bending moment due to dead load equals to, using formula, minus 1 by 12 into 5.81 into 2.86 square. Here 5.81 is factored dead load and 2.86 square is effective span square. On putting values, we will get minus 3.96 kilonewton meter. Now, bending moment due to live load equals to minus 1 by 9 into 6 into 2.86 square. Here 6 is factored live load and 2.86 is effective span square. We will get value minus 5.45 kilonewton meter. On totaling, we will get minus 9.41 kilonewton meter. Therefore, in this way, we have calculated bending moment at particular point for different cases. Now moving to next step, calculation of main reinforcement. Calculation of EST at span F. Now moment at F is 8.87 kilonewton meter and then calculate percentage of reinforcement. It will be calculated by using table and it is given in page number 48 IS 456. In this table, for different value of mu upon BD square ratio corresponding to Fy, find the value of PT. It can be get directly or by interpolation. Mu upon BD square equals to, putting the values of in this formula, 8.87 into 10 to the power 6 upon 1000 into 90 square. We will get 1.095. And for Fy 415, we have percentage of steel PT equals to 0.325 percentage. Now formula for calculating of EST equals to PT upon 100 into B into D. On putting the values in this formula, we will get 292.5 mm square. Now we will calculate spacing. Formula of spacing equals to 1000 into AST upon capital AST. Small AST is called area of steel of 1 bar and its formula is pi by 4 into 10 square equals to 78.53 mm square. Now putting the value of small AST in spacing formula, we will get spacing equals to 1000 into 78.53 upon 292.5. We will get spacing 268.47 mm. Therefore, provide 10 mm diameter bar at the rate 260 mm center to center and we will calculate AST provided for this spacing and we will get 302 mm square. Always remember, AST provided is somewhat more than AST required. Now AST at G, interior span. The value of bending moment at G is 7.05 kilonewton meter. Similar way, mu upon BD square is calculated and its value will be 0.87. For Fy 415, percentage of reinforcement of steel is equals to 0.255%. Now we will calculate AST by formula 0.255 upon 100 into 1000 into 90. We will get 229.50 mm square. Therefore, we provide 8 dia bar at the rate 210 mm center to center. For AST provided equals to 239 mm square. Now at B, next to end support, bending moment value at B is 10.20 kilonewton meter and this bending moment is negative. Now we will calculate mu upon BD square and we will get 1.26. For Fy equals to 415, percentage of reinforcement is 0.38%. Now again we will calculate AST and we will get 342 mm square. Now at negative support, we provide bent up bars. The function of bent up bars is act as a shear reinforcement, therefore provide to resist negative moment, and it is always provided at top. Therefore, to provide reinforcement at B, then we have to see that already how much bars arises from G and H, and to find how much is the requirement, and if we subtract those, then how much required to provide bent up bars. Therefore, 50% bent up bars are available from F. We will calculate value 302 divided by 2, we will get 151. And 50% bent up bars are available from G, and its value is 239 by 2 equals to 119.5. Total AST will be 270.5 mm square. Therefore, bars required at B will be 342 minus 270.5. We will get 71.5 mm square. This means that we will provide reinforcement at B only for 71.5 mm square AST. Therefore, provide 8 mm dia bars at top. Therefore, small AST equals to pi by 4 into 8 square equals to 50.26 mm square. We will calculate spacing using formula small AST upon capital AST into 1000. We will get 701.95 mm. Now, therefore, provide 8 dia bar at the rate 700 mm center to center. For AST required equals to 71.8 mm square. Now at C, why AST is provided at C? Because it is not the support same as B. Since B is next to end support but C is interior support, because the bending moment coefficient at both support, interior support and next to end support is different. Therefore, at C, mu equals to minus 9.4 kilonewton meter. Now we will calculate value mu upon BD square. Putting the values, we will get 1.16. Percentage of reinforcement will be 0.345%. Now we will calculate AST and we will get value 310.5 mm square. AST available from G is taken 50% and its value will be 239 by 2 equals to 119.5. AST available from H is taken as 50% equals to 239 divided by 2 will be 119.5. On adding these two values, we will get total AST will be 239 mm square. Therefore, bars required at C equals to 310.5 minus 239 and we will get 71.5 mm square, similar in last case. Therefore, provide 8 dia bar at the rate 700 mm center to center. For AST provided equals to 71.8 mm square. Next step is calculation of distribution reinforcement. Distribution reinforcement means load on main reinforcement is distributed by distribution reinforcement. It is given in page number 48 of IS 456-2000. Now, minimum reinforcement equals to 0.12% of steel of BD for FY 415 and 500, and minimum reinforcement equals to 0.15% steel of B into D is for FY 250. Now in this question we are taking FY equals to 415. Therefore, we will use AST equals to 0.12 upon 100 into 1000 into 115 and we will get 138 mm square. Therefore, provide 6 mm dia bar at the rate 200 mm center to center for AST provided equals to 141 mm square. Now, detailing of one bay slab. At mid span F, 10 mm dia main bar is provided at 260 mm center to center. Now at G, distribution steel of 6 mm dia at 200 mm center to center is provided. Now at B and C, 8 mm bar at 700 mm center to center is provided as bent up bars. This is all about the calculation of one-way slab. Now in next lecture, we will calculate two-way slab. We will design two-way slab. Thank you, students.